My name is Iman Mossavat. I work for ASML Research. I work mostly on optical metrology. That's where you hit some very small target with light, and you look at the response of the target to light, and from that you try to infer what you're looking at. So you fit some model to the data. You look into patterns of how targets are excited with light, and a lot of it's essentially an area where physics, signal processing, and statistical inference come into together. Yes.
So give a warm applause, please.
Yeah. So this goes. Yes, so I'm going to talk about compressive sensing. This is if you have, especially if you have a high-end digital camera, DSLR, you see that your sensor produces really large images, raw images, maybe 30, 40 megabytes, and then you can compress them into order kilobytes. And that allows us to transmit things very fast. The point is that if you could have such a successful compression, if you want to veer a rather pessimistic view of it, is a failure of sensor design in a way. So you've measured a lot of things that you're going to discard later, right? So it's actually the success that's the issue, depending on how you look at it. And when this becomes an issue, when resources are scarce. So if you have a big DSLR, you don't have a problem. But there are many cases where this becomes a problem. So this is a compressed sensing where not only now you sense things, but you're also compressing right. So your sensing hardware is compressing your data. It doesn't really measure the object. It measures certain type of information about the object that is already compressed. And then you have to actually do an act of reconstruction that is harder than essentially decompression here. So here you have a large number, and then you go to a small number, but here you already have that. Okay, so this is compressive sensing. So it's essentially going right in the hardware and changing the hardware such that you measure in a compressed way. Why that matters? So an example is MRI. So you can have an application such as pediatric cases where your patient is non-cooperative, so it will wobble a lot in this MRI, it would blur the image. So you cannot tell them to just hold their breath for 2 minutes. It's not going to work. So they're lowering the times that the resource you want to save is time. Okay, so you cannot put your camera on a tripod and wait here. You don't have that time. So you can go from order minutes to order seconds. That really opened a whole new application. How you do it? MRI measures a Fourier transform of a signal. That's basically just looking what kind of sines and cosines are in your signal. And each of them is like a 2D Fourier transform. And MRI measures the whole thing. But now we just subsampled it, right? So we measure lower frequencies a lot and like randomly measuring high frequency without any pattern. Actually, it shouldn't have a pattern, as a matter of fact. So it should be random, which is also a bit strange. But now, essentially, simply by measuring less, you can save time. And later, you spend time on processing things. Another example is a more constructed example. You have this object, say L. This object itself is sparse, so K is the number of non-zero elements. Everything else is 0. This line is a measurement mechanism. So you multiply this by a random pattern. That's what comes out. This is masking. And then you look into how many bright pixels come out. And that's your measurement. So that's one measurement. Instead of each measurement could have been a pixel. So if this random pattern was 1 pixel, this would have been a pixel value. And then you needed for every pixel, you needed a measurement. But now the measurements are mixing signal from many different pixels, right? So you can have other different random patterns. So every column is a different measurements, right? So in this case, M is the number of measurements, so the number of columns you have. K is the number of non-zero elements, so how many elements are carrying information. And N is the total space that you're looking at, so the number of pixels. Another example is more common maybe in data science, is more a data science-y, is in painting. So you have a full matrix and you can simply save time by not measuring everywhere, so by mixing some of these pixels. This is an example that you see a lot in recommender systems, where you have a big matrix that's incomplete, right? So you have seen some of the movies, but there are movies you're interested but you didn't see. And essentially by filling that matrix, they're gonna guess whether you would be interested in a certain movie, yes or no. So there would be, for example, different movies and different people, and you would have a empty matrix or a very sparsely filled matrix that you will fill in. It's the same thing as in painting. And that problem also appears here. So that's a mathematical problem. Here you also may want to avoid some measurement of some of these pixels. So your hardware is built such that you just subsample. So far, the summary is that compressive sensing shifts the complexity from sensors, hardware, to algorithms. So you would have cheaper hardware, faster hardware. You would kind of save time on the operation of the hardware, and then you do things in the computing infrastructure. This is, later in the application I can talk a little about it. This can create kind of the market, it can affect the risk of potential competition, so people can come with weaker sensors and start competing with you by more heavier algorithms. Depending on the application, gains can be from 2 to 10-fold, right? So MRI, as I mentioned, I have talked about it. The Internet of Things is another one, so you can have a ton of sensors all over. They don't have a lot of power. And that's the resource you want to essentially save. And for example, if you don't have a lot of pixels, if you don't use your analog to digital converter a lot, because analog to digital conversion wastes a lot of energy, so if you could use that less, you would reduce the energy consumption. Super resolution is exactly the other direction. Here, you're gonna take your time, you're gonna measure more, such that you can increase your resolution. So now you can have microscopes that go beyond the physical limits of a microscope can do by measuring more, right? So then now you're essentially trading off temporal resolution, how fast you can measure, with a spatial resolution, how close you can measure. That's the type of trade-off you're gonna make here. Okay, the two pillars of compressive sensing is the prior knowledge. So this should be very well known in this community, I think. And incoherent measurement, by incoherent, I don't mean it in the optical sense if you happen to have that background. Incoherent means that you're gonna, just like this example with the L, you're gonna not measure pixel by pixel, but you're gonna measure a whole lot of things in one shot together, right? If there is a time at the end, I will talk about an example of incoherent measurement at the end. But for now, think about that example with the L, where you don't measure mix of different aspects of the signal every time. So prior knowledge, the field that started with the sparsity became official compressive sensing as a sparsity. This is a very old technique. This goes, I think, maybe 70s or so. In around 2006, there was a mathematical breakthrough that they could prove theorems about the performance of this, so it became an official field. But it was there for a very long time. People just didn't know how it works, right? So then there were guarantees came forward. And now, today, we go beyond this assumption of a sparsity to generative models. We push performance forward using deep learning, but as usual, we lose all we don't know really again how it works. So we go back to the 30 years ago, right? So when we know how deep learning works, then we could also get our guarantees back. But that's the situation now. So these are the two pillars. Let me explain the sparsity a little bit. So if you have a signal F, you can have a representation of it, X, that is essentially a representation if psi here is depending on what this matrix is. For example, this can be a bunch of sines and cosines in its rows, then you can get a Fourier transform here, right? Or this can be wavelets and you get a wavelet transform. So this is your signal of interest. This is the representation of that. And here imagine this signal f, where in the Fourier domain is very sparse. So it's just have a few spikes, right? Sparse means 0 in some representation apart from a few values. Now, suppose I'm going to sample it in a very irregular grid, right? In a very irregular way. From that, can I reconstruct, right? Okay. So if I now reconstruct that with least squares, this is a linear problem, as I can show. If you do it with least squares, it's completely messed up. So if you sample irregular in a not with the right frequency, which would be your Nyquist frequency, then you can't reconstruct. But if you now tell him this was a sparse signal in the Fourier domain, you can exactly reconstruct. So without any error, right? So that's actually the great thing about it. But in reality, signals are not generally sparse. So you cannot find a representation that is a sparse. So when I saw the title of the previous talk, working in theory and broken in reality, I thought that's really ironic that that's just before this talk. So, but this is really the case. So signals are power law, so things are not really a delta function and a few non-zero values. You get these histograms where you have a lot of big values, but you also have a lot of small values that are not ignorable, right? You don't have only zeros and big values. So that's the reality of it. Now, if I go to the sensing problem, so what this hardware does, I can also think of sensing also as a linear operator. And depending on the hardware, you can find what linear operator it is. So for example, if phi is sinusoids, then we are sensing in the Fourier domain, then you build a nice MRI, right? If phi is integrating the signal over the area of pixels, then you have pixelated, so maybe you have a CCD. And if you have super pixels, then that's another example, right? So essentially, what this does in some very crude way can be a linear operation. And here is the whole thing. So your actual signal by some linear operation goes to this y, then this signal can have a representation. So you can put these two equations all in all, and this is the measurement values you get out of this sensing problem, and you have to come up with x. You know phi and psi. So at the end, compressive sensing just solve a linear problem. So there hasn't been any breakthrough in linear algebra for I think decades or maybe a century. And then suddenly in 2006, a mathematician of first grade, I mean, actually a few of them, they figured out this is actually an interesting problem. And they find out exactly that you can exactly solve this when you don't have enough equations, right? So that's the whole point. You don't have enough equations because this A is short and fat. So you get a very long signal A, a very large number of entries here, and just a few elements there. That's the catch. Again, if I look into this example, what you have here is that if I just want to map it to the equations I show you, here psi is the identity matrix because the signal itself is sparse, so you don't have to go to a transformation. This mask phi is randomized, right? So, and A is just phi. Okay. So essentially, in a nutshell, you solve a linear system where essentially the number of measurements and the number of unknowns are not matched. You have way more unknowns than measurements. The trick is that A is just not a mathematical thing, is forced by your hardware. So your hardware is dictating part of this. And that is a kind of a big deal. And then not every A allows you to work. So if signals are apart from each other in the X domain, when A is applied, they should still be apart from each other afterwards. Then they call it restricted isometry property, RIP. And that's the type of things that the mathematician would come up with, RIP. But basically it says, an example is that if you have a completely random matrix, you need a certain number of measurements. And this number of measurements just grows logarithmically with number of pixels. That's fantastic. So if you order million pixels, this is log million, right? It becomes 6 or so. So of course, this is just a bound, but it's scaling very nicely with n. It scales linearly with k, and that's the number of non-zero elements in your representation. So you at least have to have that many. If you want to try something in scikit-learn, as I show you shortly, if you solve L1 reconstruction problem, you essentially can do this. So L1 parallelization is the kind of prior you use for compressive sensing, and L2 parallelization is the standard ridge regression, which you see that in this case where you have a very sparse signal, it really doesn't work, but for L1 parallelization, it does work very nicely. What you see here is that this problem that we want to solve, so we want to find x such that y equal to x, and the L0 norm is minimum. L0 norm is the number of non-zero elements. This is a nightmare to solve because you have to find which subset should be non-zero, everything is zero, and it's kind of the NP-hard problem. So when x grows, you're hopeless, right? You put your GPUs, you just grow linearly in front of this. It would dwarf you. This means that it's just finding a needle in a big haystack, right? It needs resources. And if you have enough measurements, and that's the mathematical breakthrough in 2006, then you can solve another problem. You can solve the L1 norm problem instead of finding L0 norm. And L1 norm means that just take the absolute values of the entries of x, sum them up, and this should be minimum. And this happens to give you the exact solution of the very difficult problem. So you solve in linear time, so in polynomial time. So in polynomial time, you can solve this problem, you get exact solution. The catch is that you need this many certain number of measurements. And A has to have this restricted isometry property. So this means that you still find the needle in the haystack, it's just a very big needle, right? So if I want to look in this direction, so if I don't have enough measurements, if my number of measurements is less than my number of non-zero elements, essentially I'm looking for a black cat in the dark room, right? It's what you call overfitting, right? You just find something because you have the complex model and not enough evidence. This is impossible in the information theoretic sense. You can just not do that. If you have enough measurements, so if the moment m passes k, you go through a phase transition. Suddenly now you can find it, it's just very hard to find it. So there is no polynomial time algorithm to do this. And if you have even more, at some point you will go through a second phase transition, which allows you then to actually solve it efficiently. Now, why this is so important? This is important because it tells us what is a hard problem. It marries two very different fields. One is about computational complexity and big O notation, things that people do in computer science, which I know not so much actually about it. And one is about statistics, information theory, right? Where there is more information, it has an impact on the numerical complexity. So it brings really these two fields close to each other, which is a very phenomenal thing. By the way, this has nothing to do with only compressive sensing. It's a global phenomena. We have seen many, many problems. They have this control parameter where when you increase, you first go from impossible to possible, but very hard, and then easy. So this is again, k divided by n is your probability of non-zero values. M divided by n is the measurement rate. And you see this different phase transition for different type of signals. So the signals we are discussing here is just sparse signals. And so for a certain rate, certain number of k divided by n, you have to go here and see how many measurements you need relatively, such that it works. And this has a very interesting related with statistical physics. I'm not a physicist, by the way, but I'm always fascinated by physics. So the same mathematics that governs why things are in liquid state when they're warm, and then you can get this super cooled state and then go to the solid state, has the same mathematics that you have in algorithms. And the mathematics behind it is free energy. So if you have worked with variational autoencoder, you're actually having bounds that are approximating this. And that's the mathematics that is governing all of this. So here is a histogram of the number of non-zero elements, so how rich is the signal, and you see that signals are not sparse. You can have even 60% non-zero elements, right? So this means that you would need a lot of measurements to measure them. So if I go to this curve and say, okay, I just have a signal that has 20% non-zero, you already need half the number of pixels you need measurements. So it's not that good, actually, in practice. Right? So it's all very nice and sexy. At some point, you can exactly reconstruct, but at which point? That point can actually be not so great. So for a relatively sparse signal that's just non-zero 20% of the time, you have to still measure half of the time. You just can get a factor 2 improvement. Not so great, right? So, and this is what L1 norm does, and this is what a more complicated prior does for you. So you can use neural network to create more complex prior. Instead of saying that, hey, I have a signal that in some transformed domain is mostly 0, you can say I have certain nonlinear manifold that I'm going to learn that from the data, and my signal is on that manifold. So find the point on that manifold that give you these type of mixed measurements. And then you can see something that L1 totally failed, they can work. And then this is variational autoencoder, and then you can have even fancier methods like uncertainty autoencoder that is matched to this problem with information theoretic reasoning to work much better. So you can go below, and here you actually pumped more information to your problem. So so this is a bunch of different algorithms, but I'm going to the next slide and just basically say, in lots of applications, right, so you have a lot of field knowledge. You know a lot about your domain. But now these days people say, oh, give me a lot of data and I'm going to ignore that. So the whole thing is to come with this best of both worlds strategy where you use your field knowledge, but you're also using data together. And that's actually the evolution that you see in the methods that are used for compressive sensing. So people started with model agnostic methods when they try to use deep learning, and here you have data extensive method, you have low bias, you have flexible neural networks that do reconstruction for you, but they have no clue that they're actually solving a compressive sensing problem. You don't use anything about what you know about compressive sensing. On the other case, you have a simple model that is based on a sparsity, so it's really heavily based on what you know. In this, there is a domain in which your signal is sparse and so on and so forth. So, and then interesting thing is that there are mix of this. So here you have more complex priors than the sparsity. For example, you say that wavelets have certain properties. And in the mix, here you have neural networks whose architecture is designed based on compressive sensing algorithms. This is the last slide. There is an algorithm called approximate message passing. If you have been working with probabilistic method, you know about belief propagation. That's a method is used often on probabilistic graphs. And AMP is essentially belief propagation on a steroid. So it's kind of, a very fast approximation to belief propagation. And now we have changed the equations of AMP to fit a neural network instead of these certain equations. So there are certain terms in AMP in AMP equations where we change this very rigid term that is in the AMP algorithm, we convert that to something that it can be learned by a neural network, and that works very good. So it's a mix of all the equations that would work for AMP that is designed to solve a compressive sensing problem, but they are adjusted, some terms in those equations are adjusted to use a neural network instead of, for example, some operator, right? And then you get the best of both worlds. So you get a system, for example, that you can, if you change your sensing matrix, it will still work. And you can see that in terms of time to reconstruct is much faster than the other things for inference time. And PSNR is better. So this is at different rates of measurements. So here you measure 25% of the time and 10% of the time. So it measures faster. It measures, it reconstructs faster. It can work with less number of measurements at a better SNR, but there is no guarantee anymore. So you throw all the mathematics into a trash can. that's a pity. So I hope that changes. And pretty much that's it. So if there is any question, I would be glad to answer. Oh, you throw that. I'm very bad at that. It's safe. Okay, safe distance.
Thanks for your presentation.
Yes.
It was a lot of information, but I really liked seeing a lot of things I have seen passing by, and now having them all connected in a sense. So that's what I liked about the presentation. So,
Thank you.
if I understand correctly, in compressed sensing, you have some sparse domain that you try to sample, right? And then you have this one slide where you also showed the digit data set. And there you also have this thing with the variational autoencoder. Because
Yes.
I think a lot of neural networks also, if you bring your dimensions down in the middle, they also do some kind of encoding. So I wondered, how does it actually work? Because in all the other compressed sensing, you kind of like define your transformation from the sparse domain to the non-sparse domain yourself, but now with this one, the neural network can learn it, or how does it work precisely?
So it really depends on which one you consider this. I actually have UAE in the back of my mind better. So you remember that you pick some transformation psi, and that will give you something that's a sparse, right? So there is this domain, either you go to Fourier domain or wavelet domain, and by magic you get something that's sparse. And we know in reality that doesn't happen, right? So let's train a psi that gives you something very effective. And here they actually have a cost function. So they have a kind of encoder-decoder strategy where the encoder is linear and the decoder is nonlinear. And the encoder works such that given the encoder, you have maximum information about what is outside. So that the cost function is not minimizing MSE or other variational bound. You try to essentially say, I'm going to find directions that give you maximum information about what came in. And then you use that to essentially reconstruct what is coming out. So you pick this particular domain.
Mm-hmm.
Yeah.
Okay, thank you.
Yeah. Oh, yes, and the very back here. Can you pass it, or I can bring it to you?
We'll hop it.
Okay. Okay. Yes.
Thanks.
Yeah.
Great presentation. So you had this slide where you have the kind of the extreme and all models in between, right?
Oh,
so
yes.
At the end.
The last slide, yes.
Yes, this one. So maybe a question, which part of the spectrum would you recommend to be? Is there a specific part that you say, okay, you should always be here, or it depends on your application?
Yes.
How would you?
Yes, it depends on the application. So I think if you're brave and you can take the guarantees out and pay when you're in the production phase, then you may want to go for deep learning. But sometimes this is the only thing that would work because you don't have enough resources on a device to do reconstruction. So for example, if you want to do reconstruction, these are done by heavier hardware. So if you want to work at edge, you are forced to do that. But if you have the time, then the question is that how much you want to compress. So I think if you really want to go to the extremes of compression and time, you would be forced to work with deep learning sometimes. But if you're in MRI, I'm not sure if that's what you want to do. Maybe you play with it, but I don't know. Actually, you should know that better because you're in Philips. So
We can discuss later, yeah.
yes.